Welcome to section 11.3. We're doing inference about two means, independent samples. Okay, so just kind of a public service announcement. In this class, we're only going to look at populations that have different or unknown standard deviations. And when we do that, we're going to do something called Welch's approximate t. If this is not our class, but if the populations had the same standard deviations, we would use a pooled t statistic. But we don't do that in this class, and we'll see where that comes to play a little bit later. I'm crossing that out. So this is not in this class. All right, so we're going to be looking at populations that have unknown standard deviations or different standard deviations. And again, if that's the case, we're going to be using something called Welch's t to create the sampling distribution of the difference of two means. So we have lots of variables because it's independent. So we have n1, n2, mu sub 1 from our population, sigma sub 1. So that's all that first. So simple random sample of size n1. Population has unknown mean mu sub 1, unknown standard deviation sigma sub 1. And then same thing for population 2. Sample size is n2. Mean is mu sub 2. Standard deviation is sigma sub 2. Populations are either normally distributed or our sample size are large. That's our central limit theorem. Then we have our test statistic. Notice we're still taking the difference of means minus the sampling distribution of the difference of two means, that mean and that standard deviation. And then our degrees of freedom is going to be a little bit different. It's the smaller of the n of the sample size minus 1 degrees of freedom. So whatever one is smaller, that's the one we're going to use. Okay, so let's look at our first hypothesis test. So we're going back to state quarters and traditional quarters. He randomly selects 18 state quarters and 16 traditional quarters and weighs each of them to get our following data. And we're going to test the claim that state quarters have a mean weight that is more than traditional quarters at the alpha equals 0.05 level of significance. And then they told us that the probability plot of the state quarters and the traditional quarters indicates that the population could be normal. All right, and here it is. Okay. So a couple of notes. First of all, we know that this is definitely an independent sampling method because there's no way we could match up the quarters because the sample sizes are different. So that's one way to tell that it's independent sampling automatically. Let's talk about the degrees of freedom. It has to be the smaller of the sample sizes, and so the smaller between 18 and 16 is 16. So the degrees of freedom is 16. We take the smaller sample size. Okay, so we also have our box plot that tells us that there's no outliers. And remember, if we weren't given this information that the population could be normal, we would need a large sample size. So N1 and N2 would have to be greater than or equal to 30. And we can get that under these assumptions on the next page. It's the same assumptions that we have each time for the mean. So samples are obtained using a simple random sample. The samples are independent, so that means n sub I stands for 1 or 2, is less than 5% of whatever population it came from. The populations are normally distributed or the sample sizes are large. Sample data is approximately normal with no outliers, and each sample is no more than 5% of the population. That's going back to that. Oh, actually, no, I made a mistake. Sorry, samples are independent. They're talking about the sampling method. What a mistake I made. And then that belongs down here. Sorry about that. All right, moving on. Determine the null and the alternative. We'll do it in for the state and classic quarters. So your null hypothesis and your alternative, we're going to be comparing their means, and we say, again, that the state quarters have a mean weight that is more than traditional quarters. So you can always start off by writing what we're claiming. You can use 1 and 2. I use state and traditional. And remember, your null hypothesis is your statement of equality. All right, so there you go. Level of significance is normally given to us. 0.05 is kind of the standard. And we could use one of our stats. We could put the state quarters in list 1. We could put the traditional quarters in list 2 and get our mean and standard deviation. Once we have the mean and standard deviation, we could plug it into our test statistic, and we get 2.53. That's us right here. So now the question is it in the critical region? In other words, is it unusual? In other words, is it statistically significant? And we do that in 2 ways, the classical approach or the p-value approach. So let's do this quickly. The critical value, we look at the t-table based on our degrees of freedom and our alpha. And we're in a right-tailed test. So looking that up, t sub 0.05 is 1.753. So our test statistic is 2.53. So that's definitely to the right. It's definitely bigger. So T naught is in the reject zone. So T naught, which is 2.53, is bigger than T sub alpha, 1.753. So we're in the critical region. P-value approach. Right-tailed test, so it's area to the right of our test statistic. And then we see if that area, that probability is low or high. All right, and we're going to use our calculator to help us out on that. But for now, we would get that the p-value, I'll tell you the test to get this in just a second, is 0.009. We would compare that to alpha, and it's less than alpha. All right, so again, that's telling us that T sub alpha is all the way over here. So again, that puts T naught test statistic in the critical region. So if it's in the critical region, we know that we reject the null. So that's what we're going to do. And if we reject the null, that means we have what kind of evidence? We have sufficient evidence. And we write out our long conclusion. We have sufficient evidence. At the alpha equals 0.05 level of significance to conclude the alternative. And that was that the mean weight of the state quarters is greater than the mean weight of the traditional quarters. All right. So again, nitty-gritty, all the details in that one. Let's see another example, And let's answer it how you guys would answer it on a quiz or an exam. So we have that the researchers conducted a randomized double-blind study. So we skipped that definition earlier. It means that neither the individual nor the test administrator knows who gets a drug and who gets a placebo or sugar pill. So in this study, it was done to measure the effects of this drug on patients diagnosed with bipolar disorder. A total of 115 patients with the diagnosis were randomly divided into two groups. Group 1 received that much a day. Group 2 received a placebo. The effectiveness of the drug was measured using the Young Mania Rating Scale total score, with the net improvement in the score recorded. The results are presented in the table. Does the evidence suggest that the experimental group experienced a larger mean improvement than the control group at this level of significance? Whew. Okay, so first of all these patients were randomly divided into two groups. First of all, that tells us that it was an independent sampling method. We know we're doing a hypothesis test because we're given a level of significance. So you guys would write out your phantoms, and then P would be the mean. And it's two means in this case. You have your experimental group and your control group. So your parameter is two population means. And I would write the sampling method. And this first step right here, independent sampling, this helps you figure out where you're at that chart that we passed out in class. Okay, and we want to know, does the evidence suggest that the experimental group received a bigger improvement? So did the experimental group, was the drug effective? All right, so what we're stating, we can call this population 1, population 2. So was the mean improvement bigger than the control group that just received a placebo? And so then your null hypothesis is just that they're the same. The drug had no effect. All right, so let's move on to our assumptions. So for your mean, simple random sample, independent sampling method, N1 and N2 are less than 5% of all patients with bipolar. I'll write it like that. And then finally, the last thing is, our data normally distributed? Is the population normal, or do we have a large sample size? And we have a large sample size, right? 55 is greater than or equal to 30. Our next sample size, 60, is greater than or equal to 30. All right, and name that test. This is how we're going to get the test statistic and the p-value. Two populations. We're using our t-distribution, and it's test. So 2 SAMP t test. So let's